If you film two billiard balls colliding according to Newton's laws, or a particle obeying Schrödinger's equation, you can play the video forward or backward, and the physics remains perfectly valid. Almost every foundational law in physics is entirely reversible. But when you look at a heated block of metal on a test bench, reversing the film shows heat spontaneously flowing out of a cool room to warm the block. That breaks the second law of thermodynamics. It is the one physical rule that enforces a strict boundary between past and future. That one-way flow of energy, from a concentrated hot state cooling down into the ambient room, is a statistical inevitability. You are watching the thermodynamic arrow of time unfold on a workbench. In the 1870s, Ludwig Boltzmann realized that systems move towards disorder for a very specific reason. Disordered microscopic arrangements vastly outnumber ordered ones. If you map out the possible microstates of a mixed gas or a cooled cup, there are billions of ways for the molecules to be scrambled, and only a tiny fraction of ways for them to be neatly segregated by temperature. Entropy increases simply because probability demands it. But if entropy always rises, tracing that arrow backward creates a boundary condition puzzle. For entropy to still be increasing today, the universe must have begun in a state of extraordinarily low entropy 13.8 billion years ago. Cosmologists call this the past hypothesis. The early universe was a hot, uniform plasma, which actually represents a highly ordered, low-entropy starting point once you factor in gravity's inherent tendency to clump matter together into stars and black holes. So when an engineer measures a heated component equalizing with room temperature, they are documenting a local, small-scale manifestation of the exact same statistical rule that has driven the evolution of the cosmos. Translating that cosmic arrow into mechanical constraints began in the 19th century with physicists like Lord Kelvin and Rudolf Clausius. They established two mathematically equivalent statements: the Clausius statement, which proves heat cannot flow from cold to hot spontaneously, and the Kelvin-Planck statement, which dictates that no engine working in a cycle can turn all its incoming heat into useful work. Doing useful work requires a thermal gradient. As you can see with this demonstrator, the flywheel only turns because energy flows through the machine between two highly specific temperature reservoirs, a hot source and a cold sink. This chart plots the Carnot efficiency ceiling. It proves that the maximum possible efficiency of any heat engine is a hard mathematical limit dictated entirely by the temperatures of those two reservoirs, measured in Kelvin. The larger the temperature gap, the higher the ceiling, but that ceiling will always sit below 100%. Every piece of thermal machinery ever built operates inside these margins. Whether designing a cryogenic plant, a steam cycle, or an internal combustion engine, you are constrained by the exact same ceilings established over a century ago. For an engineer, the second law does not act as a helpful guide for building a better machine. It dictates exactly how good better is physically allowed to be. To measure the tax extracted by that physical limit, engineers track an irreversible process. When a component cools, plotting its temperature against time reveals the exact curve of a system drifting towards thermal equilibrium with its surroundings. This is a bench test cooling curve plotted against time. Where the line flattens out and meets the room temperature grid line, the system has reached maximum local entropy. The thermal gradient is gone, and no more useful work can be extracted. The thermodynamic rules governing a lab bench copper block today are identical to the ones mapped out for heavy machinery, like this 19th century steam engine. The scale changes, but the absolute limits do not. Engineering success is measured by calculating these theoretical floors and designing physical processes that approach them as closely as possible, knowing they can never actually be crossed. In 1867, physicist James Clerk Maxwell proposed a thought experiment that looked like a genuine loophole in these rules. He imagined a tiny being operating a frictionless door between two boxes of gas. By letting fast molecules group on one side and slow ones on the other, this demon seemed to create a temperature difference out of thin air, lowering entropy without doing any work. It took nearly a century and the development of information theory to close that loophole. Physicists Leo Szilard and Rolf Landauer proved that to sort the molecules, the demon has to acquire information and eventually erase its memory to measure again. This animation illustrates the Landauer limit. It shows that the logically irreversible act of erasing a single bit of information mandates the release of a small, temperature-dependent amount of heat. The entropy removed from the gas by the daemon is fully matched by the entropy generated when its memory is wiped. The daemon is not a loophole. It is proof that information is physical. Computation is tied to the exact same thermodynamic reality as a mechanical engine. When we zoom in even further to the nanoscale, classical thermodynamics requires a statistical refinement. According to the Jarzynski equality and the Crookes fluctuation theorem, a tiny system can experience moments where its individual molecular trajectories show a brief decrease in entropy. This does not break the second law. The system merely undergoes a highly improbable statistical fluctuation. This is where the Landauer principle meets real-world hardware. Even in modern silicon DRAM cells measured at the single electron level, engineers find that actual memory operates above the theoretical Landauer floor because a practical cell cannot be prepared in perfect thermal equilibrium. Researchers are actively testing new definitions of entropy production for small quantum systems to map out the microscopic foundations of the physics. But at the macroscopic scale, the reality of the classical laws remains completely uncontested. The second law of thermodynamics acts as the absolute boundary condition for physical design, locking in the performance of everything from power plants down to the memory chips inside your computer. To review the mathematical limits of modern hardware and read detailed thermal engineering case studies, visit our website and see how these thermodynamic ceilings are mapped out in the lab today.